I would like to thank the organizers, Professors Griffiths, Katsarkov, and Aguilar for the invitation. Sorry, I'm unable to be there in person. So my talk is just a Blackboard talk, but done on a piece of paper via Zoom, since I belong to the School of Primitive Visual Aids. So what I'm talking about is joint work with Terry Napier, and I'll describe what motivates the question I'm talking about. So it's based on the question of Shafarevich, or actually also called conjecture. So it's is the universal cover of a smooth projective variety holomorphically convex? So let me just remind you of the definition of holomorphically convex. So So let X be a complex manifold. We say, so first of all, so let K contained in X be compact. So we call the holomorphically convex hull, or holomorphic hull of K to be, so let's say we'll call it K hat. So this is just the supremum on K for all F holomorphic on X. So we say, so let me just, X is holomorphically convex, which I'll just denote like this. If for every K compact, K hat is compact. So it just means that your complex manifold has an abundance of holomorphic functions if it is non-compact. An alternate statement is also the following. So it turns out to be equivalent, but a non-trivial theorem that X is holomorphically convex if and only if X admits, I'm assuming everything is non-compact and connected, a proper holomorphic mapping to a Stein space. So the biggest problem we have is if you start with a complex manifold, especially non-compact, it's a difficult problem to try and say that they have non-constant holomorphic functions, or when does that happen? These are all, in fact, even for an open Riemann surface, this was a theorem only in the 1940s by Benke and Stein. So a natural question then is to ask, if you certainly don't know how to approach Shafarevich conjecture, can you look at some consequences of it and say maybe you could try to attempt to prove that directly? So that's what I want to talk about. So let us say X smooth projective. I look at the universal cover of X. So this is so then you have a proper map to a Stein space. So you, in particular, if it's holomorphically convex. So if X twiddle is holomorphically convex, then we have a proper map to a Stein space, and we can assume the fibers are connected by just Stein factoring it. So now we can try and look at the consequences. So let's look at the situation where Y is, the Stein space is two-dimensional or higher. So one of the features of a Stein manifold or Stein space is going to be that holomorphic functions extend across compact sets. So, which of course, so we can try to prove that directly. So let us say, so let's start with the following. So let's say what happens if Y is one-dimensional. So we have a proper map to a Riemann surface. Then we cannot extend holomorphic functions across compact sets. So in fact, we will have the first cohomology, in fact, of X twiddle, let's say compact supports, is not going to be 0. So ideally, what you'd like to do is to say that, the only obstruction to say vanishing of first cohomology with coefficients in the structure sheaf, compactly supported cohomology, it's non-vanishing, we would like to say, is only due to the fact that your manifold maps properly onto a Riemann surface. So we'd like to try to understand this. So now I look at the following situation. So I have X, say, smooth projective. I have the universal cover. So I need some way of trying to actually attack this question when we don't have holomorphic functions or methods from, say, complex variables to attack these questions. So I'd like to use an idea of Bochner. So to do that, I would probably have to, let me explain what I want to do next. So first remark is, because X is smooth projective, or let's say compact Kahler, you have the following. The fundamental group certainly has to have its abelianization, its odd Berry numbers are even. So in particular, so we look at the simplest case. So we want to know when X twiddle has a, let me explain what I mean by that, positive Green's function. So positive Green's function just means there is a right inverse to the Laplacian on the universal cover. I mean, you fix a Kahler metric on X and you pull it back to the universal cover. And you want the right inverse to be, that thing to be given by actually a positive function. So that's what I mean by that. So it turns out it's a theorem of Varopoulos. Showed that existence of positive Green's function is equivalent to the fundamental group having more than quadratic growth. So anyway, the consequence is if the fundamental group does not have Z cross Z as a subgroup of finite index, the universal cover always has a positive Green's function. So in the case the fundamental group has Z cross Z as a subgroup of finite index, then the universal cover essentially maps properly onto C. So that means we can just ignore that situation. So we look at the situation when we have a positive Green's function. Okay. So I'm going to. So I'd like to. So the vanishing of compactly supported cohomology with coefficients of structure sheaf is equivalent to just solving the D-bar equation for 0-1 forms with compact support. So you start with, suppose, say alpha is a 0-1 form with compact supports on X twiddle, such that D bar alpha is 0. So you'd like to try to solve for alpha in terms of a function. So what you try and do is, so you look at alpha and you remove it. So you subtract off the harmonic projection. So this is the stuff of essentially due to Codera. So this is the harmonic projection. So then the existence of the Green's function will tell you that you can solve the equation up to some scalar factors, which I won't worry. So if you just solve this equation. So the main thing you will know is, so the issue is, of course, having, so this means what? So P alpha is a 0-1 L2 form on X twiddle, and it is D closed and D star closed. So in particular, it's an anti-holomorphic 0-1 form. So if you take its conjugate, so if you look at P alpha conjugate, so this, so let's call it beta, is an L2 holomorphic 1 form. On X twiddle. Now we use an idea of Gromov's. So Gromov's observation. So first of all, on X twiddle, since beta is closed, beta is D of H, where H from X twiddle of C is a holomorphic function. So now we try to solve for, so the main observation of Gromov is because DH is in L2, so if you compute the DH squared, the integral, so it'll turn out to be just integrating over C of the volume of the fibers. So what this will say, sorry, not F, it's H. So Gromov's idea, so Gromov's point is, so this means that so almost all fibers have to have finite volume. And because the universal cover will have bounded geometry, so you'll have uniform size for holomorphic coordinate charts, you will get that the fibers' finite volume subvarieties are automatically compact. So this is of course assuming beta is not 0. Because finite volume implies compact. So then you can show that all fibers, therefore from there we can conclude This requires a little bit of work, that all the connected components of the fibers of H, sorry, are compact. So you can Stein factor this map. So once you Stein factor it, therefore Stein factoring H gives a proper map from the universal cover. You can show it has to be the disk because the finite energy condition. So you get a proper map to the disk. So in which case, of course, you can't expect to solve d bar with compact supports. So therefore, what we have shown is if this beta happened to be non-zero, then you have a proper map to a Riemann surface. So now what you can do is, so that's where you get the dichotomy. So if beta is 0, you get the following. So that means this harmonic projection is 0. So we have actually solved G applied to d bar star alpha is alpha. And you would like to say that, so you like to somehow say that then d bar star alpha, G applied to d bar star alpha has compact support. So we need an argument. So first remark is, since alpha is compactly supported, G applied to d bar star alpha is holomorphic outside a compact set. And further, G applied to d bar star alpha goes to 0 at infinity, the same as G going to 0 at infinity. So it's the behavior of G that determines it. So what we can do is the following, by considering, so the way Bochner dealt with this situation in Cn for n greater than or equal to 2, so there you have a Green's function, which is 1 over absolute value of the distance between 2 points raised to the appropriate power. So it'll vanish at infinity. So what you will end up doing is you will take a projection, you'll take a coordinate function. So and then restrict. You'll notice that some of the level sets of your coordinate function will be disjoint from the support of G applied to d bar star alpha. Support of the one form alpha. So that means you will have some holomorphic function, which when restricted to the fiber will vanish at infinity. And that will contradict the maximum principle, and therefore it will vanish. So that's how you end up proving compact support nature of G applied to d bar star alpha. Now, in our case, we don't have a holomorphic function to play this game. However, what we can show is the following. We can show that natural log applied to G applied to d bar star alpha with a negative sign is spluri superharmonic, whatever that means. But anyway, the main point is it has this property and goes to infinity along every sequence on which G goes to 0. And that immediately turns out to lead to a contradiction. So this leads to a contradiction. And so then what this will imply that G applied to d bar star alpha had to be compactly supported. So in this proof, what have we used? We have only used the fact that our Kahler manifold, whatever the largeness and infinity of a covering of a compact manifold. We've used the fact that you have a positive Green's function. And we needed to know that closed forms were exact. So this is just the first de Rham cohomology being 0. So therefore, we can conclude by this argument. Conclusion is, suppose X is a complete Kahler manifold with bounded geometry. That just means largeness at infinity. And let's say H upper 1 of X is 0. So remember that the compactly supported cohomology vanishing is mutually exclusive with respect to mapping properly onto a Riemann surface. So we get X maps properly holomorphically onto a Riemann surface. If and only if this is 0. So this, of course, requires, the first de Rham cohomology is 0. I mean, one can ask similar questions about intermediate covers, so which may no longer be Galois coverings and things like that. So we can't apply other results about relationship between finitely generated groups and existence of positive Green's function. So this was the motivation for the question, and we wanted to sort of then deal with a little more general situation. So what happens if first de Rham cohomology is not 0? So the main problem we have then is you have this harmonic projection, and what will happen is all you can say is G applied to d bar star alpha is pluriharmonic outside a compact set. So not, all these arguments that we use will not work. I mean, so you have to do something more. So that's where I want to introduce the notion of filtered ends. So anyway, so one of the things we notice from this, the theorem first proved by Arapura, Bressler, and myself using ideas of Gromov, that the universal cover of a smooth projective variety or compact Kahler manifold has at most one end. So this proves that, because what did we show? If H1 de Rham is 0, then X maps properly onto a disk, because you're going to get a proper map to connected fibers to a Riemann surface. The Riemann surface has to be simply connected. But since we have, if you have a L2 holomorphic 1 form, it's going to be exact, and the holomorphic function will then descend to the disk. So only the disk has holomorphic functions with finite energy. So let's look at what happens when. So the next remark is, of course, this is all interesting only when we deal with the one-ended situation, because the following shows that. So the following is a standard counterexample going back to Cousin. So what he says is, Cousin says is, you take C star cross C star, and you quotient out by a cyclic group, Z acting here, where the one acts on ZW by multiplication by lambda and mu. Lambda and mu don't have absolute value 1. You want them to be multiplicatively independent. So that means this will then cover product of two elliptic curves, and the covering group will be Z. So in particular, it will be a two-ended covering. And this covering then so this is just the answer to the question, would intermediate covers be holomorphically convex? So in particular, so if I call this X, X has no non-constant holomorphic functions. This is because any holomorphic function is just going to be a Lorentz series in two variables, invariant under scaling, multiplication by lambda and mu. And the multiplicative independence guarantees that, they cannot, the only thing that's available is constant. So that's, but also this example is two-ended. So clearly you cannot have H1 with compact supports with coefficients of structure sheaf being equal to 0, because then that would imply that you can extend constant functions along the ends, 1 and 0, and you'll get a holomorphic extension, which we know is not possible. So let's analyze what is going on. So let's assume, say, bounded geometry. Positive Green's function. So then what do we do? So if you have alpha, which is, say, compactly supported on X, then we look at alpha minus the corresponding harmonic projection, and you write it as T bar of something using the Green's function, and the U will have similar behavior at infinity as the Green's function. So what we can do is, so first thing we'll have is U is pluriharmonic. Outside the support of alpha. So what you might try is the following. Okay, so U could be complex valued. So U could be of the form U1 plus I U2, let us say. So it's pluriharmonic, but U1 is real and then U2 is real. So now what we can show is the following. So let's also assume for the moment X has one end, say. So what happens? I mean, so you could have U1 and U2 to be linearly dependent. So essentially, U is given by a real function, which has the same behavior. So now what is very interesting is, okay, so if are linearly dependent over R, so one is just, because they're real functions, then you can say the following. So then it turns out X has a neighborhood of the end, let's call it, say, E, with the property that it requires a bit of an argument, but so what we can show is with the property that pi 1 of E does not surject. Onto pi 1 of X. So this is where the notion of filtered ends show up. So, okay, so what do I mean by that? So this was a notion introduced by Ross Gagan. So let me remind you, how do you describe the ends of a ends of a topological space? So it's just the space of ends, whatever is just pi 0 of x minus k. Say you're taking the limit over all k compact. So you're just counting the number of components at infinity or whatever. So you can now play this game for maps too. So supposing you have a map f from x to y, we can talk about ends of f. So this will be the limit again over k compact. But now you take pi 0 and you take f inverse of x minus k. So you take the complements, take the pre-image, and then try to understand the number of components. So it's certainly so if, for example, if x has one end, it certainly will imply that neighborhoods of ends can, the fundamental group cannot surject. So in particular, so we will define, so the x is just going to be so you look at the map from the universal cover of x to there, so call it pi. So then it's just the ends of pi. So that means what you're doing is you look for compact subsets of x whose complement is has no relatively compact components, and then you take the pre-image of those things upstairs and then keep doing it. So it turns out there is an interesting structure theorem you can prove under this assumption. So first thing is, so if x is a open Riemann surface, so we will denote this by E twiddle of x. Okay. So in particular, you can have something with one end with many filtered ends. So that's Riemann surface. Then E twiddle of x is going to be 1, 2, or infinity. If it is 2, it's going to look like that Cousin example. No, not for a Riemann surface, I'm sorry. Let me just take a step back. So anyway, the following theorem was proved by Napier and myself. Again, X a complete Kahler. Bounded geometry. So if E twiddle of x is greater than or equal to 3, so you can have, it can be any number you want in the general case, only on a Riemann surface. Do you have these restrictions? Then x maps properly holomorphically onto a Riemann surface. So interesting enough, in that Bochner-Hartogs dichotomy, where I was showing that this end, it's pi 1 does or neighborhood does not surject onto pi 1 of x. You can show in that situation. So in this situation where u1 and u2 are linearly dependent, you can still show that x maps properly onto a Riemann surface. So then the question becomes, if u1 and u2 say are linearly independent. So what you can show is, So what had happened was we had to split it into two pieces, two style of argument. So anyway, let me just state the theorem. So this is the theorem I want to state. So X is going to have X is complete Kahler with bounded geometry and say one end, and has one end. Then X maps properly holomorphically onto a Riemann surface if and only if this is not zero. I have to also assume X has a yeah. So I have to assume that it has a positive Green's function. If I don't, then I don't know how to do it. So the part that is open is if you remove the assumption of positive Green's function, can you still get somewhere? So that is, you don't know how to do it. So let me just outline how sort of this proof goes. So we start with this. It's always the same process. So you start with d bar u equals alpha minus p alpha. So this is where you use the Green's function. Now, as usual, the issue is if p alpha is, if the harmonic projection is zero, then the earlier argument I said works. So you can just show that u then would be compactly supported. But what happens if you have an L2 holomorphic, L2 harmonic 0, 1 form, which is, and if you take its conjugate, it will be an L2 holomorphic 1, 0 form. So we have to deal with two cases. So first question is, suppose the Green's function does not vanish at infinity. Originally, we didn't know how to do this case. And it turns out this case is much easier than the case where the Green's function vanishes at infinity. So let me outline what the point is. So if the does not vanish at infinity, so you can, the whole point is, if it's really a kernel, it's a function of two variables. So if it does not vanish at infinity, so that means there is some sequence along which it does not go to zero. So you take, so what you can show is if you take that sequence, so let's say y nu is the sequence along which this does not go to zero. Then by using a subsequence, by letting a subsequence of this go to infinity, you can find h of x, which is the limit as nu sub k goes to infinity, is going to be a positive harmonic function, positive pluriharmonic function. Sorry, it requires some work, but which does not have finite energy. So I just mean the differential is not an L2. So then what you can show is the following. You can show that if you take the, so this will be a holomorphic one form. So if you wedge it with P alpha conjugate, you can show it 0. So we can show this. So the idea is not very difficult. What you do is you look at roundy H wedge D bar H wedge the Kahler form to the n minus 2, and you can integrate by parts by applying a cutoff. So you can work it out. So you can show that this would have to be 0, and then from there you can read off everything. So now, because roundy H is not L2, and P alpha closure, of course, is, conjugate is an L2. So you have a pair of holomorphic one forms whose wedge is 0 and they're linearly independent. So it turns out you can apply the same Gromov style argument and prove a Castelnuovo-de Frankis theorem in this L2 context. So this then can be used to show if P alpha is not 0, then X maps properly holomorphically onto a Riemann surface. So now then we deal with the Green's function going to 0. So it vanishes at infinity. So now you see, remember we had that U1 plus IU2 earlier. So U1 and U2 had this pair of. So if they're linearly dependent over R, so one is just a multiple of the other, then you can again show that X maps properly onto a Riemann surface. So we will sort of say, let's write it out. So they're real. So then X maps to a Riemann surface properly, holomorphically. Now, because remember they are pluriharmonic, so if roundy U1 wedge roundy U2 is 0 on the complement of support of alpha, because U1 and U, now you're assuming U1 and U2 are linearly independent, you can still modify the Castelnuovo-de Frankis kind of argument, and then you can map properly onto Riemann surface. So the case happened that, if roundy U1 and roundy the wedge is not 0. So if the wedge is not 0, so now you have to do some work and try and show that you can. Essentially, the idea is you'll be in a situation which used to be called, I think Grauert calls hyper n minus 1 convex. And so that is enough to get sort of, you'll get a contradiction to the fact that you have a positive Green's function. So you play those two together and then do that. So that's how the theorem goes. So the question open is, so it's just saying that the potential theoretically the infinity is small. So usually it's called, so in potential theory it's called parabolic, but parabolic is used for so many other things. I didn't want to sort of mention it. So this is where I'm stuck with. So anyway, thank you very much for your time. Sorry.